Welcome to Trane Engineers Newsletter Live. I'm Jeannie Harshaw, and today we'll discuss controls communication technologies. The marketplace demands open standard communication protocols to deliver flexible and interoperable control systems for building owners. Recent innovations in the industry have made this even more prevalent. On today's program, we'll start with a discussion of the BACnet communication protocol with an emphasis on specifications to ensure the needs of the owner are indeed met. Then we'll discuss various wireless communication options and where each best applies. And finally, we'll wrap up with a comparison of wired versus wireless communication. Today, we have Trane application engineer Dan Kalaji and a product manager from the cities, Jim Cole, to walk us through these topics. Dan, can you get us started?
Sure. One of the most common questions that I get from specifying engineers is, what should I write in a specification so that the site will have an interoperable BACnet automation system? It's a difficult question to answer because there is no silver bullet. Every building and campus is unique, as are the needs of the customer. However, there are some common characteristics in a well-designed automation system that will meet the needs of the customer on day one and also be able to evolve in the future. But let's first talk about the BACnet Standard. The standard is over 1,300 pages long. It's primarily a nuts and bolts document that prescribes how the BACnet protocol works and how it must be implemented. The features defined by the standard are intended to scale from the most simple devices, such as a temperature sensor, to an enterprise automation system that may control and monitor hundreds of sites. Aside from the minimal amount of core functionality that's required to be a BACnet device, all the functionality is optional. So a vendor can decide what functionality to include in their products. The set of features they choose to implement will change based on the intended use of the device. It's important to remember that no device implements all the features of BACnet. The functionality needed to implement the temperature sensor is much less than the functionality needed for a building controller. The BACnet standard was never intended to be a guide for engineers on how to specify automation system. So the responsibility falls on the specifying engineer to know enough about the functionality of BACnet and how the protocol is intended to be used so that you can correctly specify a system. So our goal today is to help you understand a little more about BACnet and what items to specify so that you can do this. We'll start by introducing the concept of BACnet device profiles. A device profile is an easy way for an engineer to define the overall scope of the device's functionality. Each profile is comprised of 5 functional groups: data sharing, alarm and event management, scheduling, trending, and device and network management. The thing to remember about device profiles is that they define a minimum set of functionality using BACnet interoperability blocks, or BIBs. However, most vendors will include additional BIBs to make their devices more feature-rich and better able to meet the customer's needs. When you are comparing 2 devices that support the same device profile, you will need to look deeper to determine if the 2 are actually equivalent by comparing the BIBs that each device supports. The standard defines several device profiles, but 5 are most commonly specified. For equipment, the ASC and AAC profiles are most often used. The BC profile is focused on building system control devices, and the OWS and AWS profiles focus on operator workstation functionality. Let's start with the equipment-focused profiles. The ASC, or application-specific device profile, is targeted at a piece of equipment, like a VAV box, fan coil, rooftop unit, or water chiller. This profile requires support for sharing data between devices. This allows a supervisory device, such as a building controller, to read and write data in the device. It also is required to support the device and network functionality that allows it to participate in a device discovery process, which is a core functionality of BACnet. The thing to remember when specifying device profiles for equipment is physical size or complexity of the control sequence doesn't matter. The profiles are focused on BACnet communication functionality. They are not equipment focused. For example, a makeup air unit can supply thousands of CFM of air, but it's just a box with a fan and a damper. The controller doesn't care if it uses a 1/4 horsepower motor or a 20 horse motor. All it knows is if I energize the fan output, air will flow. The AAC profile, or Advanced Application Specific Device Profile, is also targeted at equipment, but includes extra functionality that supports alarming and would allow this equipment to run in a standalone mode. So the functionality specified here is the same as in the ASC profile device, plus support for alarming and scheduling. Since I just mentioned it, let's talk about alarm and event management for a moment. There are 4 types of event reporting defined in BACnet: change of value event reporting, intrinsic reporting, algorithmic reporting, and alert reporting. I'm not going to get into the details on each one, but I do want to point out that when someone says, I want BACnet alarming, they are referencing the intrinsic reporting functionality. This is used when you want to monitor analog or binary sensor data. For example, there is a temperature sensor in the space, and you want an alarm generated if the temperature falls below 60 degrees or rises above 80. The generated alarm is sent from the device that detected the condition to a supervisory device that would store the alarm message in a user-readable log. In this case, the alarm originates at the equipment level controller because that's where the physical sensor is attached. So if the equipment controller doesn't support intrinsic alarming, you have made it much harder for the B-AWS integrator to provide the alarming functionality that the customer is going to expect. Intrinsic reporting is the easy button for alarming, and every device in the system should support this feature.
So Dan, you showed that intrinsic alarming is a requirement of AAC device profiles. So does that mean we should be specifying only AAC devices for equipment control?
No, not necessarily. If you do that, you are also requiring support for BACnet scheduling. That's probably overkill for equipment like a VAV box or fan coil and adds unnecessary costs to the project. Many vendors choose to also include intrinsic alarming support in their ASC profile devices because it's such a common requirement in the marketplace. So if you want support for alarming, don't discount ASC devices out of hand. When you're writing a specification, just be sure to require intrinsic alarming support. This slide shows 2 examples of spec language that you could use. The next profile is the building controller profile. Devices that meet the BC profile are intended to perform system monitoring and control, like a system-level controller that coordinates the operation of VAV boxes with an air handler, or the coordination of chillers, pumps, and cooling towers in a chiller plant. A BC profile device must support BACnet scheduling functionality. This allows the device to coordinate the behavior of the equipment in the system through the use of time and day schedules. Without a system-level device to do this coordination, the building won't function as desired. Notice for this profile, the ability to trend data is also required. This makes sense for this type of device because the collection and storage of performance data is a valuable feature when you need to analyze or troubleshoot the system. Remember, there is nothing that prevents a vendor from supporting trend log functionality in an AAC or ASC profile device, and many do so. It is just not required that they do so. The last 2 profiles are the Operator Workstation and the Advanced Operator Workstation profile. These are not BAS devices like equipment or the building controller. Instead, workstations are software applications that run on a PC or computer server. They are intended to be used for remote monitoring and control and can connect to potentially hundreds of sites and store large amounts of historical trend data. The workstation allows a facility manager to monitor and control all the buildings it can connect to. Common examples are college or medical campuses with dozens of buildings, or a national chain of restaurants with hundreds of locations.
So it sounds like the device profile does not apply too often for small sites.
That's right. Very rarely do you need a workstation-level device to control a single building or even a few buildings. The reality is most single building sites can be controlled with a web page-based user interface served from the building controller. If you need to specify a BACnet workstation, both of these profiles require a very similar set of functionality. The difference is the depth of the functionality provided to perform remote BACnet troubleshooting.
So if the functionality is similar, how do you know which profile to specify? The OWS or the AWS?
If the intended user of the workstation knows HVAC equipment and controls, and their focus is to keep the building running and the occupants happy, then the OWS profile is sufficient. If the user also needs to remotely solve complex BACnet issues, then I'd recommend the AWS profile. Here's a good rule of thumb. If the user doesn't own a copy of the BACnet standard, choose the OWS profile device. The AWS workstation is targeted for a BACnet super user. But even for the super user, 99% of the time, the OWS profile device will meet their needs.
All right. Thanks, Dan. The next topic we'll discuss is BTL certified devices, what they are and where you can find them. But first, just a little background on BACnet International and BACnet testing laboratories. BACnet International is the trade organization that represents BACnet in the marketplace. Its primary responsibilities are to promote all things BACnet and then validate that it's being implemented correctly by its members. They also publish a quarterly magazine and maintain a website that has useful information for specifying engineers and BACnet product developers. The challenge with implementing any standard is, if there isn't an independent expert verifying that a vendor implemented it correctly, how do you know they did it right? As Dan mentioned before, the standard is 1,300 pages long, and there's plenty of room to get it all wrong. BACnet International wanted to drive acceptance of the protocol by making sure the standard was implemented correctly. To do this, they needed a formal and independent test process, which is why BACnet Testing Laboratories was created. BTL manages protocol compliance testing activities worldwide, as well as the device certification process. Certification is awarded after a formal test process verifies that the functionality that a device supports is implemented in accordance with the BACnet standard.
So what does certification mean to you? When you have a device with BTL certification, you know that an independent lab has tested this device using a standardized and repeatable process to verify that the supported BACnet functionality works as expected. Without certification, you have a trust me it works device. As a general statement, there is more risk using a device that is not BTL certified. At this point, I want to take a sidebar and talk about how BACnet is often marketed in the industry. Beware of marketing slang used by salespeople to get around the question of BTL certification. You may hear phrases like native BACnet, BACnet compliant, supports BACnet, or other variations of this theme. None of these terms mean anything to indicate the quality of their BACnet implementation or the functionality they support. There is no BACnet International or ASHRAE recognized definition of these phrases. Often they are used in hopes that you are not educated enough to ask the question, are your devices BTL certified? If the answer is yes, you can ask for their certification document or go to the BACnet International website to verify the device is listed. If the answer is no, I'm not saying that you should immediately disqualify that device, but there is more inherent risk, and I think you owe it to your customer to do a little more digging. BACnet International maintains the official list of BTL certified devices on their website. On this site, you can click on the BTL listed products from the menu and access this list. Once you find the device in the list, you can view the protocol information conformance statement. This document contains detailed information about the object types supported and the building blocks or BIBs used to implement the functionality in this device. In addition to this listing, the vendor is authorized to display the BTL certification logo on its device, and it can use it in marketing literature.
So BTL certification is important to ensure you get what you're expecting when it comes to BACnet. Next, staying on that theme of how BACnet is often marketed in the industry, we'll discuss the difference between two communication technologies, BACnet MS TP and BACnet IP.
Traditionally, BACnet MSTP has been used to communicate between the equipment controllers and the building controllers. However, some vendors promote the use of BACnet IP at the equipment level of the network architecture, even suggesting that engineers require this in their specs. Before you do this, it's important to know the pros and cons to each implementation. For those of you that may not be familiar with these terms, BACnet MSTP uses an RS-485 communications protocol. The network gets created using twisted 2 or 3 conducted shielded cable with a drain wire. The devices are all wired together in a daisy chain configuration, and most sites use either 76.8 or 38.4 kilobaud rate for transmission data. BACnet IP uses the Internet protocol for communication. The network is created using Ethernet cabling with devices connected using home run wiring back to an IT hardware switch. And the data is usually transmitted at a 100 megabit baud rate. I thought we could use a matrix to see how these two stack up against one another. In the left-hand column, I've listed 7 criteria to compare. There may be others, but I think this list provides a pretty broad set of criteria. The first criteria we'll look at is speed. This is the big selling point for IP at the equipment level. Some will promote that MSTP is so slow and that IP is so fast. I can't argue with that. A protocol running on a 76.8 network is going to be much slower than a 100 megabit Ethernet network. I've got to give this check to IP for this. But now let's talk about why the need for speed. I'm going to generalize and say that 90% of the time a BACnet packet, regardless if it is communicated on RS-485, Ethernet IP, or with 2 cans and a string, is less than 100 bytes long. Ethernet IP was designed to send megabytes of data at a time and is optimized to do that. In the world of building automation, we sample a space temperature sensor once every 2 minutes. Does the user really care if it took a microsecond for the data to be transmitted across the wire or a few milliseconds? I don't think so.
So Dan, is there any circumstance when I would want that speed?
The comment I always hear for wanting Ethernet IP is, what if I want to download new software remotely to the device and the file contains megabytes of data? Yep, that's a valid reason for wanting it. But my question is, how many times is software actually downloaded to an equipment controller remotely? The most common answer is never. And if you ever did need to download software, do you want to risk downloading it remotely? I wouldn't, because I know something will go wrong, since it always does, and if I lock up the device, I'm not there to fix it. So IP is faster, but the benefits of having that speed are minor. Let's move on to the next criteria, which is device cost. You can buy an RS-485 transceiver chip for about 50 cents. The hardware for an Ethernet interface transceiver is about $2.50. That's the component cost, but we all know there's a markup added to the finished product. If you assume a 200% markup, now my RS-485 transceiver costs $1, and the Ethernet interface is $5. There will probably be at least 2 additional markup costs before the device gets installed, so $1 becomes $3 and $5 becomes $15. When you have lots of units like a VAV box or fan coils, the cost difference really adds up. So for device cost, the advantage goes to MSTP. The next criteria is wire cost. The twisted pair is less expensive than Ethernet cable, and the time it takes to put a Phoenix connector on a twisted pair using a wire stripper and a screwdriver is a lot less than fanning out the 8 wires in an Ethernet cable and using a special tool to put the RJ45 connector on each end. So wire cost is less for MSTP. How about infrastructure cost? As an example, let's say we're going to connect 40 VAV boxes to the network. With twisted pair wire, I just need to daisy chain from one box to the next and eventually to the building controller or to a BACnet router to make the connection to the building controller. With Ethernet cable, I need to pull wire from each device to an IT hardware switch somewhere in the building. I know that home running them back to one big IT switch would require a lot of contract labor. So let's try to reduce that by installing 4 smaller switches throughout the building. But they cost $100 a piece, so there's another extra $400. The reality is, it's probably still more expensive to home run back to these switches when compared to daisy chain wiring. So infrastructure cost is less with MSTP. Now on to network reliability. For a daisy chain network, if a wire is cut, on average, half the devices on the network will go down. If I cut an Ethernet cable, I only lose 1 device. But what about those 4 switches I installed? If one of them fails, I lose 10 devices. The switches also add 4 additional points of failure in the IP network when compared to MSTP. To take this a step further, what would happen if the IP network goes down in the whole building because a router somewhere failed or the network was hacked? With MSTP, the devices are connected directly to the building controller, so it will still be able to control the equipment and the spaces will remain comfortable. But because the building controller uses a web browser interface, I won't be able to monitor the building remotely. However, if the VAV boxes are connected with Ethernet IP and the network goes down, the building controller can't communicate with the equipment controllers. So there is no system-level control and no way to monitor the building. For this one, it's hard to pick a definitive winner. So let's just give each protocol a check. The next criteria is security. With the Ethernet IP solution, the controller on each of those 40 VAV boxes has an IP address, which means it's potentially accessible to anyone who can log onto the network from anywhere in the world. But if those VAV boxes are connected using MSTP, someone would have to be direct connected to the network to gain access. So for security, the advantage goes to MSTP. Finally, how about IT department support? In most companies, the IT department is known as the department of no. You ask for something, and their answer is usually no. How happy do you think they will be when I ask for 40 static IP addresses for my VAV boxes? Probably not very. I wonder what they will say when I tell them that I put 4 unauthorized IP switches on their network, which I bought at the local electronics store. If I use MSTP, I need 0 IP addresses, and I don't even need to talk to the IT department. To me, that seems like a bonus. The other thing I should mention is that the IT network is probably not running when the building is complete. So the BIS installer can't test the system until after the building has opened. So for IT department support, the advantage goes to MSTP. Now I know I had a little fun in this exercise, but I think the end result speaks for itself. For a typical project, it makes no sense to install Ethernet IP network devices at the equipment level. If someone wants to sell you on this solution, I suggest that you ask them what we are missing in this exercise, because this seems like a bad idea to me.
Before wrapping up this section on BACnet, sometimes we don't get BACnet top to bottom in the control architecture. Dan, can you share a little bit about the gateways?
On a renovation project where the scope is to only upgrade the supervisory building controller and the front end of the building automation system, it's common practice not to replace the equipment level controllers. If the equipment controllers are BACnet communicating devices, integrating them into the new system is fairly easy. Typically, the MSTP network wire can be connected to the new building controller, and it will be able to discover and install the equipment controllers automatically. However, often the existing equipment controllers use a proprietary communications protocol. If replacing these controllers is not an option, one method of integrating them into the new system is to use a gateway device to translate from the proprietary protocol to BACnet. This allows data to be accessed by the new automation system. For some older controllers, you may find there is no gateway solution. In that case, replacement is the only option. Today, with the broad acceptance of BACnet by the marketplace, I would say that a gateway should never be allowed for new construction or even for a renovation project where new equipment controllers are being installed. Gateways create a choke point in the communications network because all of the building network data must pass through a single device to reach any of the equipment controllers. Furthermore, if the gateway should fail, you lose the ability to communicate with the equipment. A second failure mode is if the gateway device is overwhelmed during periods of high network traffic. This can result in slow performance, drop messages, and if severe enough, it may bring down the automation system. When specifying equipment-level controllers and networks, require all devices to use BACnet as their method of communication. Gateways and proprietary devices should only be allowed by exception, and then only when there is a compelling reason to do so. On a related note, make sure you don't allow a proprietary communications protocol to be used at the building network level or the enterprise level. Although that may seem obvious, I mention this because there are control vendors today that promote a proprietary communications protocol as an open communication solution. The problem is the protocol is only available with devices they manufacture, which is by definition proprietary. The devices they make support both BACnet and their proprietary protocol. They say we can do BACnet while promoting their proprietary solution as the most open solution in the marketplace. The only way to deliver interoperability between devices manufactured by different vendors is to specify that the BACnet protocol is the only method of communication allowed at all levels of the network architecture.
Thanks, Dan. If you'd like to learn more about BACnet, we suggest visiting the BACnet International website. They have online training that was designed for the consulting engineering community. And there are also white papers and other resources. So now let's transition to another communication technology topic, that being wireless communications for HVAC control. Jim, wireless is everywhere in our world, and wireless is not new to the HVAC industry. So what's changed over recent years?
Yes, wireless communication has been around the HVAC industry for decades. But early solutions did not have the benefit of communication standards that were specific to HVAC. So the applications of wireless were somewhat limited, maintenance costs were high, and reliability suffered. Today's wireless solutions are better suited to our customers' HVAC control needs. The key differences are that they can support open standard solutions like BACnet. Maintenance is minimized with longer battery life. They can operate much more reliably, and installation is easier and at a lower cost. However, it's important to understand and apply wireless technologies correctly so you can realize these benefits without compromising reliability, performance, ease of integration, or security. You've surely heard about Wi-Fi and Bluetooth, and there are other technologies now available for commercial HVAC. In a bit, I'll describe the differences in these technologies and where they are best applied. But first, I think it's helpful to differentiate the four categories of HVAC control devices: sensors or end devices, equipment controllers, building controllers, and tools. Along the top of this matrix are key differentiators for these devices like power source, the data rate or amount of data that needs to be communicated, and the quantity of devices typically found in a building. The power consumption of sensors and end devices is typically low, so long-lasting batteries or power harvesting can be used with minimal maintenance expense. These devices typically transmit the least amount of data, so a wireless solution with a lower data rate can be acceptable. And there are typically a lot of these devices spread throughout the building, sometimes requiring periodic relocation. So eliminating wiring costs for sensors makes wireless especially attractive. Equipment controllers have line power available, so power consumption is not so great a concern. But the data rate is moderate for equipment controllers, and there are often many of them in the building. This can make wireless attractive for these devices also, especially when you consider future expansions or upgrades. For the building controller, power is not a key concern since the wireless device can share the same line power source. From the building controller up, data rate is high. But from the building controller down to the equipment controllers, the data rate is moderate. So the benefit of wireless communication to the equipment controller is greater since the number of devices connected to the great network is higher. Finally, service tools typically use rechargeable batteries, making power consumption less of a concern. But support for high data rates is key to technician productivity. The ability to move around and provide service without disruption is a significant benefit of wireless service tools, especially in education or healthcare, so that the HVAC technicians can do their work without disturbing doctors and patients or teachers and students.
So I guess the point is that using wireless can provide benefits in all these devices.
Right. Wireless can provide a benefit for each of these 4 categories of HVAC devices, but the needs are different. Before discussing how to choose the best wireless technology for application in these different devices, I want to quickly introduce various topologies since they impact this decision. The most common wireless topologies are point-to-point, star, and mesh. Remember the old tin cans we used as telephones when we were kids? Well, at least when I was a kid. Point-to-point is very similar. Direct communication between 2 devices except without the wire. Some things to note. All else being equal, this topology will provide good performance and low power consumption because we're only sharing information between 2 devices. However, if the wireless link breaks between these 2 points, we lose communications since there's no other path to get the message through. Star topologies are all around us. Examples include the wireless cable or DSL modem in your house, your wireless access point at work, or at a public hotspot. In all these cases, the modem or access point is tied in some way to a wired backbone. From there, our wireless devices like a laptop or a wireless printer can communicate wirelessly to that one access point. One way to think about this is several point-to-point topologies connected to a central node. Note that this is still dependent on a single wireless path. Like point-to-point, if that path fails, there's no other path to get the message through. Last is wireless mesh. You can see what we mean by mesh just by looking at the picture. There's typically multiple possible communication paths. In this case, the blue circles indicate routers able to route messages throughout the network. Mesh networks self-form. A potential path between any 2 devices is available when they're within wireless range. This also allows the network to self-heal. If a communication path is lost, the device searches for a different path. The green circle represents the network coordinator, which is typically wired to a building or system-level controller. The orange circles represent end devices. These devices are typically battery-powered using replaceable or lifetime batteries. They're intentionally kept out of the message routing area to minimize their power consumption. In a real-world application, the routers are located on the equipment controllers. The end devices are sensors, and the coordinators is located on the building controller. Mesh topology is superior in that it's the only self-healing topology, providing multiple paths between all devices within wireless range. This results in the best possible reliability. To demonstrate, here's an example building with a rooftop VAV system. Note the wireless communication path between the rooftop unit controller and the building controller, and also the paths between the VAV box controllers and the building controller. Whenever a faster or stronger path is available, the network automatically reroutes the message. In this case, the wireless signal from the rooftop unit is routed to the nearby VAV box onto the building controller. So with mesh networking, it's possible to have higher levels of reliability than conventional wired systems. With that brief background in topologies, let's take a closer look at common wireless technologies and how some are better choices for different applications. As I said, Wi-Fi and Bluetooth are well known. You may have also heard about the Ocean Alliance, Z-Wave, or Zigbee. While these competing technologies are evolving, the current capabilities vary significantly. So knowing the differences is key to knowing how to best apply them. I'll use this matrix to compare signal range, data rate, topologies, and power use. Starting with Wi-Fi, its key advantage is its high data rate or bandwidth, up to 600 megabits per second. This makes it an ideal replacement for where Cat5 or Ethernet wire would be typically used. Think BACnet IP communications. Wi-Fi offers good signal range, but it only supports point-to-point or star topologies, and power use is high, so batteries may last for only several hours. Since Wi-Fi communication is available in virtually every building, it could also be tied directly to the wireless LAN. However, many customers or IT leaders prefer to reserve the wireless LAN for their business operations and customer access. Many are also concerned that using that network for HVAC control might compromise service levels and security. Consequently, a separate virtual private network on the existing wired network or a separate wired network is usually preferred for high-speed networks. So Wi-Fi is really best suited for building controllers and maybe some equipment controllers that require a high data rate. Common Bluetooth solutions use the point-to-point topology and can now operate up to 25 megabits per second. And while most provide a 10-meter range, the latest technologies can operate up to 60 meters away. Bluetooth's high data rate and point-to-point topology make it ideally suited for technician service tools, since it's isolated from the customer's wireless LAN, where sensitive information could be accessed. Note that Bluetooth does not support standard BACnet communication. The Ocean Alliance was started by a company called Ocean, based out of Germany. It has extremely low power consumption and power harvesting capability, such as solar cells. But the data rate is fairly low, and it can only support point-to-point topology. This makes it ideal for lower power, lower data rate applications like sensors and end devices. But the limited data rate means it's not suitable for communication networks, and it does not directly support BACnet. Z-Wave technology supports wireless mesh and draws very little power, meaning that batteries can last for years. However, its lower data rate limits its application. So it's best suited for sensors and end devices, and also gets used in residential applications. Also note that Z-Wave does not support BACnet communications. Zigbee offers a good signal range, moderate data rate, supports the mesh topology, and has low power consumption. It also supports BACnet communications. This makes Zigbee ideal for sensors and end devices, equipment controllers, low data rate service tool applications, and even for communication up to the building controller. Its low power consumption has made over a 15-year battery life possible on temperature, humidity, occupancy, and even CO2 sensing. Trane's analysis and experience has demonstrated that Zigbee can be a single solution for tools, sensors, equipment controllers, and for communication up to the building controller. The advantage of a single solution is that it simplifies and reduces the cost of installation while reducing wireless traffic.
So I heard there are important differences between wireless technologies. Some are better suited for different applications in the world of HVAC control.
That's right. For example, Wi-Fi is an ideal replacement for Ethernet cable due to its high data rate. But its higher power consumption makes it less ideal for battery-powered devices. Bluetooth is an ideal tool or technology for service tools due to its small network support, moderate data rate, and broad availability on mobile devices. And Ocean's extremely low power consumption make it ideal for low data rate battery powered devices like zone sensors. And Z-Wave's lower data rate and low power consumption make it ideal for residential applications. Zigbee's moderate data rate, BACnet support, mesh topology, and low power consumption make it ideal for sensors and applications where MSTP wiring is used, like for communication between equipment controllers and the building controller.
So earlier, Jim, you showed the benefits of mesh topology. How about signal range? How does that impact the application of wireless control? And what about security?
Let's go back to the example building I showed, which depicts a Zigbee wireless mesh network. The blue circles represents the typical signal range of wireless systems operating at power levels that are allowed globally. Note that where the circles do not intersect, repeaters will need to be added between these devices. But for some parts of the world, like in the Americas, regulations allow for an extended signal range. This means a stronger signal and lower install cost due to simplified network design and fewer repeaters in the building. Greater range also increases redundancy and reliability because it can result in as many as 4 times the number of potential paths. Before I discuss security, let me introduce the concept of coexistence. Zigbee devices are built on IEEE radios, much like Wi-Fi and Bluetooth. So they're designed to reliably coexist with other wireless communications that might be found in the building. 2 key strategies are used to ensure this. First is channel management, choosing wireless channels that do not overlap. And second is carrier sense multiple access with collision avoidance. This avoids collisions by transmitting only when the channel is sensed to be idle. For more information, I've included the Zigbee Coexistence white paper in our bibliography. But the proof of coexistence comes from many successful installations in difficult applications, such as hospitals, stadiums, warehouses, airports, fire stations, and casinos. So now I'll get back to security. Certified BACnet communications over a standard Zigbee network are required to be secured using Advanced Encryption Standard 128. What this means is a trust center will create a randomly generated 128-bit network security key for each Zigbee network. This network security key is required to decrypt communications from the network. This keeps HVAC communications isolated from confidential and sensitive information. Hacking into this system would require a Zigbee radio. These radios are not as common as Wi-Fi or Bluetooth and cannot be used to communicate to business systems, but only to other BACnet or Zigbee devices.
Thanks, Jim. So you focused a lot on wireless solutions since it's so prevalent, but are there still some cases where wired communication might be preferred?
Yes, there are a few. The first is a high electrical noise environment. A good example is a healthcare radiology room with an MRI machine. In this application, you want to use a wired temperature sensor and locate all wireless devices outside of the room. This avoids the extreme electrical noise generated by the large electromagnet. Note that in a typical production facility environments where moderate electrical noise exists from machining or common welding equipment, this is generally not a concern. The second advantage is reducing security concerns from especially security-sensitive customers, like the defense industry. And third are locations where the wiring is easy, the number of devices is limited, and the use or configurations of the building is not expected to change. A good example is a water chiller located in a mechanical room where the building controller is also installed. Easy to wire, it's never going to move. I think these applications are exceptions to the rule, though, and that using wireless communications makes sense for the majority of equipment and installations for these reasons. First is lower installation cost and faster project completion. Wireless communications reduces the time needed to pull and sometimes repair wire. This is especially true in buildings where there may be surprises inside the walls or where there may be hazardous materials that need to be abated. While the benefit of wireless may be greater in existing buildings, we see it on virtually all building projects, including new construction. On the subject of faster project completion, the Director of Maintenance for a school district in Kansas City shared that installation of the wireless sensors definitely expedited the installation process, which is a very important benefit when dealing with the small windows of opportunity like spring break, Christmas break, or summer break that we usually have to accomplish projects of this nature. On a related note, wireless can also make controls upgrades more financially feasible. Because it can allow for a phased installation, you can start with only a couple of devices and as you go. Think of a retrofit scenario where you upgrade a few VAV boxes every night. Once you just install just a few boxes, you can set up a network. As you get more installed, you can easily add them to the network. With a wired network, you would need a complete end-to-end daisy chain that is properly terminated. Another advantage is easier problem solving. With wireless, it's easy to relocate devices to improve sensing accuracy and control. This is valuable because we know we can't anticipate where everything is going to be located as we finish construction projects. As an example, here's a copy machine installed right next to the zone temperature sensor. Because this machine creates heat, we may need to move the sensor so that it can more accurately measure the space temperature. In other cases, we might want to move the sensor just for aesthetic reasons. With wireless, we can move the sensor to a better location with very little cost, improving performance or aesthetics. Wireless also means no damaged communications wire to troubleshoot. While we might think wire is trouble-free, it often isn't. Communications wire can mistakenly be cut during the project, adding cost and delaying completion. And any bad connection or compromised wire can take a network down. It's even more frustrating and difficult to troubleshoot when the failure is intermittent or if the weak part of the wire is hidden behind a wall. Remember, it doesn't matter where the poor termination or compromised wire is. In a wired installation, every device past that compromised wire or bad termination stops communicating when this happens. Worse yet, the problem can start well after the project is completed. With wireless, these problems can be avoided. And when we use a wireless mesh topology, there are multiple paths available to keep the system up and running reliably. Another advantage is that wireless devices are easy to move over the life of the building as spaces are reconfigured, or sometimes when we want to move devices for convenience reasons. Perhaps a user interface is not located where it can be easily accessed. And technicians are more productive and less likely to disturb building occupants if they're free to access the building controls using wireless service tools.
So, tying into Dan's theme of specification, what are the key things to specify so the customer can realize all of these advantages of wireless without compromising things like reliability, security, and maintenance?
I'd suggest specifying a 200-foot design range to simplify design and installation, wireless mesh to maximize reliability through redundant communication and self-healing paths, IEEE radios to support reliable coexistence, lifetime batteries or power harvesting to minimize the need for maintenance, indication of battery charge for peace of mind, and the use of open standard solutions like BACnet and Zigbee certified communications.
Thanks, guys. We hope you enjoyed the C&L program and that you found it a helpful way to learn about control communications technology. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane controls. For those of you seeking continuing education credit, be sure to check the continuing education programs, which include many past E&Ls, all free and on demand. And remember to fill out a survey and let us know what you think of today's program. AIA members, as always, please remember to turn in your information to your local site coordinator. And finally, please ask your local host about details for the remaining Engineers Newsletter Live program this year. Thanks for your time today. We look forward to seeing you next time.